Good morning all. This is Dr. Abdul Pasha, Department of Electrical and Electronics Engineering. Today I am going to give presentation for power system operation and control. The topic is optimal scheduling of hydrothermal systems. So what is hydrothermal scheduling system? So here earlier I was discussed regarding scheduling process, unit commitments, how the generators will schedule according to the load requirements or to meet the load demand, how generators are supposed to be released their outputs according to the time schedules. Here also the hydrothermal scheduling is also takes place to make the smooth working operation of the power system network. So here hydrothermal plays a key role in the operation planning of power system network. So here the main problem is with the hydro unit schedule, because here we cannot expect the continuity of the flow. So compared to the hydel, thermal can make the input to be continuous as there is a storage of coal handling plant and we can go with that inputs. So when several hydro plants are located on the same river, the water outflow from one plant may be very significant portion. So the inflow to one or more other plants which are located down the stream. So both electric and hydraulic couplings, they will create a multi-dimensional non-linear programming problems. So here the optimal scheduling of generation in a hydrothermal system involves the allocation of generations among the hydel and the thermal units. So as to minimize the total operational costs of thermal plants while satisfying the various constraints on the hydraulic and power system network. So short-term scheduling is going to be takes place. So it is normally assumed that target dam levels at the end of the scheduling period have been set by a medium-term scheduling process. So that takes into the account longer time river inflow that should be modeled and load predictions is going to be takes place. So here coming to short-term scheduling process, they allocates the water discharge, that is for hydropower generation process, the costs while satisfying various units and reservoir constraints. So here the main constraints includes time coupling effects of the hydro subproblems where the varying system load demand and cascaded nature of hydraulic network, varying hourly reservoir inflows, physical limitations of the reservoir shortage and thermal plants will going to be takes place. So here are some of the important solution methods which will include for these problems. Those are dynamic programming process, network flow and linear programming process, non-linear programming process, mathematical decomposition, expert systems and artificial neural networks. So these will play a key role while solving and giving the solution methods to one of the problems. So the mostly used three solution methods for hydrothermal scheduling problem are one of the iteration methods. They will conclude with the gradients and dynamic programming methods. So each of these method has their own drawbacks again. So based on that, we will suppose it to be opt to the best suitable methods. So in iteration method, solutions of coordination equations will use the plant generations, which will exist in outside the plant capacity, and also negative generation of the certain plants are going to be takes place. So when incorporating the limits on the plant capacity, the volume and hourly discharge constraints may take place. So the value of G would be may going to change. So this requires the scheduling of logic to adjust to the constrained variables and which does not go beyond its limits. So gradient methods were found to be the inefficient when the system size becomes too much large. So when the system size is going to be increases, then this will become so very difficult to operate. So in the dynamic programming method, with the successive approximation, it is necessary to specify the initial feasible schedule processes. So for which the reservoir is going to be happens. That means when one reservoir is scheduled while keeping the other schedule is fixed, the alternating from one reservoir to the other until specified iterations or cost difference between the two last iterations are within the specified tolerance. That means this method dispatches only one reservoir at a time. This is not flexible enough to deal with the coupling constraints. Nowadays, genetic algorithms plays a very important role. They have been used for many optimization methods or applications, such as economic dispatch, unit commitment, and like that it will be flows. So in this work, whatever the genetic algorithm approach which is developed for solving 24 hours ahead of scheduling process for the hydrothermal power systems. So here the difficulty of water balance constraints due to hydraulic coupling and water travel time, they may goes to delays and which are satisfied in the algorithm systems, which will be comparatively study made on a test system with conventional DPSA method cases. So coming to hydrothermal scheduling process, it involves the optimization of a problem with a nonlinear objective function. So with this mixture of linear, nonlinear and dynamic network flow constraints, the basic optimal hydrothermal scheduling in the short-term process may exist. So which involves minimizing the thermal cost function F over a given scheduling period, which will be subjected to the number of unit and power system network equalities. So and also it involves inequality constraints. We already discussed earlier what are various constraints they are taken place in the power system operation. So with the discretization process of total scheduling time into a set of shorter time intervals, for example, it may say 1 hour, the scheduling process can be mathematically formulated as minimal of summation fi of function ps of I comma t functional variables. So this will exist. So here it will be subjected to the following constraints. That is, one is system active load balance, total active power generation that must balance the predicted power demand plus losses at each time interval over the scheduling period. So here this will be taken as I substance to in rupees, summation of ps of I comma t plus summation of I tends to ph of I comma t, pd of t plus pl of t. This is the load demand plus actual demand of the power for a given interval of time. When it is the case of thermal plant loading limits, when it is the requirement to satisfy, then it will be associated with ps of I comma t minimal, which is less than or equals to ps of I comma t less than or equals to max case in the period of t tends to t case. Now it is the case of hydro plant loading limits. When it is the requirement to satisfy, then hydral of P can be pH of I comma T minimal, which is under the limits less than or equals to pH of I comma T, which is less than or equals to pH of I comma T max. They may exist in the period of T tends to T. So these are the period of sequences. They may exist. Next, coming to the hydraulic operational constraints, which will comprises the water balance, that means continuity of the equations for each hydro unit, as well as the bounds on the reservoir storage, and which will releases some targets. So here the boundaries are determined by the physical reservoir and plant limitations. So as well as the multi-purpose requirements of the hydro system may goes to be takes place. So these constraints includes physical limitations on the reservoir or its storage volumes and the discharge rates. So based on these constraints, these are going to be takes place. So here one of the expressions represented, that is VH of I comma T minimal to the VH of I comma T max case. This will be under less than or equals to condition. So they may exist in the period of t tends to t, small t tends to capital T. When it is the reactive power coefficient for idle case, I comma T minimal less than or equals to same reactive power coefficient under the limits of I comma T of maximum content. So they may also take t tends to t case. When it is the continuity of the equation for the hydro reservoir of the network, then VH of I comma T is VH of I comma T minus 1 plus IH of I comma T minus QH of I comma T. So here one of the subtraction takes place for the reactive coefficient with complex power for idle case with SH of I comma T, and this should be added to the coefficient of reactive term m equals to 1 to Ru QH m comma T coefficients of tau to I comma m, and also m comma T coefficients for complex power term under the limits of tau of I comma m. Next, it is the case of system spinning reservoir requirements. Then it becomes summation of I equals to 1 in rupees and PS of I comma T plus I equals to 1 to rupees hours PH of I comma T, which will be greater than or equals to R equivalent. So these are the substances they will take place. When it is the case of power generation characteristics, the power generated from a hydro plant is related to the reservoir characteristics. So based on the reservoir characteristics, we are going to decide the how much power generated during the peak demand case, as well as the water discharge rate, that also to be considered. So in general, the hydro generator power output is a function of the net hydraulic head, that is the availability of the head onto the power flow, it must be considered. So based on this head, we can decide the load demand requirement for the given system. So here hydro generator power output is a function of the net hydraulic head and reservoir volume, and also it may be the rate of water discharge coefficient, that is Q. So that is pH of I comma T as a function of all these parameters. That means head, hydraulic head of the discharge coefficient Q and volume V, and which will be as a function of I comma T, it will be the final function of H of T. So the model can also be written in terms of the reservoir volume. This will be taken instead of the reservoir net head and a frequently used functional parameter. So that is pH of I comma T as C1 VH of I comma T whole square plus C2 of Q I comma T whole square, C3 of V of I comma T, QH of I comma T plus C4 of VH I comma T, C5 QH of I comma T plus C6. All these are the coefficients which are related to the hydrothermal scheduling process, which may taken place under the functional parameters T comma capital. So in setting the generator levels for the given thermal plants, a quadratic cost function is supposed to be used here to model the fuel input power or output characteristics of thermal units. So there will be a good business practice in which the production cost is minimized without specifying the quality. So this is not any different in the power system network. The main aim here is to reduce the production cost while maintaining the voltage magnitudes at respective bus. Now coming to the planning of the optimal scheduling of hydrothermal system. So optimal scheduling of hydrothermal system is the process of allocating the power generation in between thermal and hydroelectric units. If you observe the diagram, we are allocating in between thermal and hydro plants. This is the optimal scheduling of the hydrothermal system. We are going to allocate the power generation in between this thermal and hydel plants. So this is the reason is that to minimize the total operating cost of the thermal plants. This is done while also satisfying the constraints of the hydraulic power of the entire network. So this is the thermal plant, this is hydel plant. In between your load is going to be connected. So this should be the fundamental hydrothermal system. Based on the reservoir storage, water inflow, availability of the coal here from the input section, these meanwhile process will be going to be controlled. So here the optimal scheduling of the generation in a hydrothermal system involves the allocation of generation among the hydel and thermal units. So this is as to minimize the total operational cost of thermal plants while satisfying the various constraints on the hydraulic of the power system network. So here are some basic things to consider when optimally scheduling a hydrothermal system. So what are the basic constraints here means hydroelectric generation. So by using hydroelectric generation, we can go with low cost hydroelectric generation. That should be very important to incorporate to the load requirements. So again, once again, water availability for the same hydropower plant. So how much amount of water availability that will be frequently checked for a given power system. So here optimization problem must respect water availability constraints. So scheduling period also considered. So this period can be short range, that may be in days or weeks, or longer range, months or years. And generator output limits, they may be the scheduling problem must observe the limits of the generator output cases. Again, hydraulic power flow constraints. So the scheduling problem must observe the hydraulic flow constraint problems. Environmental pollution is also one of the case. Here it is required to minimize the environmental pollution which will be incorporated into the system. And it is the case of economic distribution of loads in hydrothermal scheduling process which will be exist in between the various units of the plants. So to determine this economic distribution of load among the different units of the plant, the variable operating cost of each unit must be expressed in terms of its power output. So the fuel cost is the main criteria here. So according to that main cost in thermal or nuclear unit, then fuel cost must be expressed in terms of the power output. So other costs like operational and maintenance costs can also be expressed in terms of the power output. So fixed costs such as the capital cost, depreciation, which are not included in the fuel cost cases. So here the fuel requirement of each generator is given in terms of the rupees per hour. These are the units which may consider as the fuel requirement. Now let us define the input cost of a unit in I term in rupees per hour and the power output of the unit as a PI. Then the input cost can be expressed in terms of the power. That is Fy equals to A by 2 Pi square plus Bi Pi Ci in rupees per hour, which is treated as equation 1. Now the operating cost is given by the quadratic equation which is obtained by approximating the power in megawatt case versus cost in rupees. So incremental operating cost of each unit is calculated as lambda I dfi by dpi plus API plus BI, which is in rupees per megawatt hours. This is treated as equation 2. Now we should assume that only two units having different incremental costs supplying a load. So there will be a reduction in the cost if some amount of load is transferred from the unit with a higher incremental cost to the unit with lower incremental cost. So in this way, the load is transferred from less efficient unit to the more efficient unit. So thereby reducing the total operational cost. So the load transfer will continue till the incremental costs of both the units are continuity process in the same manner. Now this will be the optimal point of operation for both the units. So here the above principles can be extended to the plants with a total of n number of units. So total fuel cost will be the summation of individual fuel costs, that is taken place from I equals to 1 to so on up to n number of each units. That is Ft equals to F1 plus F2 plus so on up to Fn. That is taken place K equals to 1 to n Fk. This is equation 3. Now let us denote the total power that the plant is required to supply at a period of Pt, then such that total power becomes P1 plus P2 plus so on up to Pn. When we make this summation k equals to 1 to n, that will be taken place up to Pk. This is fourth expression. Next, here the variables are P1, P2 up to so on Pn are the power supplied by the n different units. So here the objective is to minimize the total cost of the fuel for a given particular period or time. So this can be achieved when the total difference, that is dft, becomes 0. That is Ft equals to F1 plus F2 plus so on up to Fn, which is equals to summation k equals to 1 to n Fk. This is treated as equation 3. So now let us denote that total power that the plant is required to supply the power in a given specified period of time, then Pt equals to P1 plus P2 plus so on up to Pn. So this variable is summation k equals to 1 to n Pk. So here the variables are called P1, P2, P3 up to so on Pn are the power supplied by n different number of units. These are the n different number of units. So the objective here is to minimize the total fuel cost for a given time period. So this can be achieved when the total difference becomes 0. When the difference becomes 0, the total period can be equivalent to making to the 0. So here the dft parameter becomes differentiation case, that is dou ft by dou p1 of dp1 plus dou ft by dou p2 of dp2 plus so on up to dou ft by dou pn into dpn, which is equals to 0. This is considered as equation 5. Now since the power supplied is assumed to be constant, then we have to write it as a dpt equals to dp1 plus dp2 up to so on dpn, which is equals to 0. This is writing as equation 6. Now when you multiply the sixth expression with one of the Lagrangian coefficient lambda and subtracting it from the fifth expression, we will get the resultant case, that is dou ft by dou p1 minus lambda of the functionality dp1. So this will be follows for the variables 1, 2, 3, 4 up to so on n. Up to n cases, this variable formation will take place. So this is treated as one of the product of dpn. When you consider dou ft by dou p1 minus lambda as a function of dp1, then it will be supposed to be follows up to n number of terms. Capital N number of terms it will be follows. So because of this, the equality in the earlier equation is satisfied when each individual term given in brackets is equals to 0. So this gives us finally dou ft by dou pi minus lambda is equal to 0, where I is equal to 1 comma 2 comma so on up to n is going to be considered. So here also the partial derivatives becomes a full derivative in nature. Since only the term fi of ft varies with the variables pi, which is I equals to 1 so on up to n, we then have one of the parameter lambda, that is df1 by dpi, which is equals to df2 by dp2, which is equals to up to so on dfn by dp. Yeah, this will be considered as equation 9. When you are going to be considering the generating limits for n number of units, then it is not always necessary that all the units of the plant are available to share a given load. So some of the units may be taken off due to scheduled maintenance, and also it is not necessary that less efficient units are switched off during the off-peak hours. So there is a certain amount of shutdown time and startup costs associated with the shutdowning process of the units during the peak of hours, and servicing it back onto the online during the peak hours case. So here, to complicate the problem further, it may take about 8 hours or more to restore the boiler of a unit and synchronizing the unit with the given bus case. At respective bus, it will going to be synchronized. To meet the sudden changes in the power demand, it may therefore be necessary to keep more units, that is necessary to meet the load demand during that given period of time. So this will makes the safety margin in generation. This is called as spinning reserve unit. So the optimal load dispatch problem must then incorporate the startup and shut down the cost for without endangering the system security constraints. So the power generation limit of each unit is then it going to be given by one of the inequality constraints. So here inequality constraint will be written as P minimum of I, which is less than or equals to Pi less than or equals to P max. So here the variables will follows from I equals to 1, 2, 3, 4 up to so on n number of units it is going to be considered. So the maximum limit for the power generation is if it is Pg max, then upper limit of the power generation capacity of the each unit must be coincides. So when it is the case of upper limit, then the number of unit sections can be subdivided for respective generator to the meeting of the load required. So on the other hand, the lower limit Pg minimum pertains to the thermal consideration of operating of the given boiler. So in a thermal or nuclear generating station, the operational unit must produce a minimum amount of power. So because of this minimum amount of power, it cannot ready to meet the load requirement. So it should not reach the load requirement of the power such that the boiler of the thermal components are stabilized at the minimum design operating temperature. So due to which the scheduling process will be very slow. So to meet all these requirements to the load requirement, we need to plan to the according to the system to meet the load requirements with the n number of generators. They are supposed to be turned on according to the scheduling process to the given load. We can make the system scheduling process easily. One of the methods of economic dispatch and unit commitment problems, they will be cumulatively considered to make all the generators in the system to run or to make turn on to the respective demand of the system. So when the generators are to be shut down or turn on, then the period of consistency in the power system network with one of the operational features they must suppose it to be considered. So according to the system requirements, they must treat to the constraints of the generators. It may be equality or inequality of the nature. So the suitability of the generator constraint is considered based on the load required. So during the peak hours or during the day demand or evening hours, the requirements may be considered. So based on that, the system constraints are going to be followed. So according to that, we may consider the system parameters and we will design. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.